In order to understand commonly used dimensionality reduction techniques such as principal component analysis, PCA, and linear discriminant analysis, LDA, we first need to grasp the concept of eigenvectors and eigenvalues. In this video, we will explore what eigenvectors and eigenvalues are and how they are obtained. If you are curious about what dimensionality reduction is, it might be helpful to watch the previous video on dimensionality reduction first. In order to understand eigenvectors and eigenvalues, you need to have a grasp of the concepts of matrices and vectors. In the subject of linear mathematics, matrices and vectors are covered, but for those unfamiliar with them, let's briefly look into what matrices and vectors are. A matrix is a collection of numbers arranged in a rectangular form, enclosed by brackets, consisting of rows and columns. In particular, when it has m rows and n columns, it is called an m by n matrix. In the example shown here, we have a 2 by 4 matrix, which means it has 2 rows and 4 columns. Additionally, a matrix with an equal number of rows and columns is called a square matrix. Here, we are showing a 2 by 2 square matrix, where both the number of rows and columns is 2. Regarding the transpose of a matrix, it refers to the matrix obtained by interchanging its rows and columns, and it is denoted by the uppercase letter T as a superscript. In this example, we have a matrix A with a size of 2 by 3. When we take its transpose, it transforms into a 3 by 2 matrix. So, if we consider one of the numbers in matrix A, let's say 1, which is located in the first row and second column, you can observe that in the transpose matrix, it appears in the second row and first column. Matrices, just like regular numbers, can undergo addition, subtraction, and multiplication. For addition and subtraction, you simply add or subtract the numbers that are in the corresponding positions. For example, when we add matrices A and B, the numbers at the same positions are added together, resulting in 4 when adding 2 and 2, and becoming 0 when adding 0 and 0. Therefore, in order to perform matrix addition and subtraction, the two matrices must have the same dimensions, meaning they need to have the same number of rows and columns. For matrix multiplication, you need to multiply the numbers in each corresponding position of the rows from the first matrix and the columns from the second matrix, and then add up the results. Therefore, in order to perform matrix multiplication, the number of columns in the first matrix must be equal to the number of rows in the second matrix. In other words, if you have an m by n matrix and multiply it with an n by p matrix, where both matrices have n as the common number of columns and rows respectively, the result will be an m by p matrix. For example, when you multiply a 2 by 2 matrix with a 2 by 1 matrix, the resulting matrix will be a 2 by 1 matrix. In this slide, the matrix I shown has 1s on its diagonal and 0s on its off-diagonal. A matrix with all 1s on the diagonal and 0s elsewhere is called an identity matrix. As mentioned in the previous slide, matrices can be multiplied. If we multiply matrices A and B, and the result is an identity matrix, we call B the inverse of matrix A. The inverse of a matrix is denoted by placing a -1 as a superscript on the right-hand side of the matrix. For reference, you can find the formula for finding the inverse of a matrix in the lower part of this slide. Next, let's take a look at vectors. The most significant characteristic of a vector is that it possesses both magnitude and direction. On the other hand, a quantity that only has magnitude but lacks direction is called a scalar. A vector can be thought of as a matrix with either a single row or a single column. We represent vectors with arrows, where O represents the starting point, and P represents the ending point. The magnitude of a vector is determined by calculating the square root of the sum of the squares of its individual components. Also, When we encounter the concept of projection in principal component analysis, PCA, it refers to the projection of one vector onto another. Let's say we have two different vectors, A and B. Projecting vector B onto vector A means finding a new vector that has the same direction as vector A, but with a magnitude equal to the distance from vector B to vector A along a perpendicular line. In simpler terms, you can think of it like casting a shadow when shining light on an object from above. The shadow falls perpendicularly downward. In the previous slide, we mentioned that we can perform multiplication between vectors, but we can also multiply a scalar and a vector together. For example, if we have a vector 1, 1, and we multiply it by 3, we get the resulting vector 3, 3. In this case, it means that the direction of the vector, 1, 1, remains the same, but its length or magnitude increases. Similarly, when we multiply a vector by a scalar, it implies that the direction of the vector remains unchanged, while its scale or magnitude changes. This aspect plays a crucial role in principal component analysis, PCA, a dimensionality reduction technique, which we will explore later on. Now, based on the concepts of matrices and vectors we discussed earlier, let's explore eigenvalues and eigenvectors. In this slide, we see the multiplication of matrix A and vector X. Following the matrix multiplication rules mentioned before, when we multiply matrix A and vector X, we get a vector with elements 3 and 3. To put it differently, this can be simplified as multiplying the vector consisting of 1 and 1 by 3. So the fact that multiplying by 3 results in the same vector direction with only the magnitude changing means that the vector's direction remains unchanged, while only its magnitude is affected. In other words, when we multiply vector x by matrix A, and the result is equivalent to multiplying x by a scalar value, we refer to x as the eigenvector, and that scalar value as the eigenvalue. Here, x represents the eigenvector, and lambda represents the eigenvalue. In summary, the eigenvector indicates the direction, while the eigenvalue represents the scale of transformation. In the context of PCA dimensionality reduction we will explain later, it is crucial to determine the directions of transformation in a way that minimizes information loss. Additionally, for effective classification, it's important to spread the data points widely without overlapping. And this is where the concepts of eigenvectors and eigenvalues come into play. Now let's take a look at how we can find eigenvalues and eigenvectors. As previously explained, when the result of multiplying matrix A by vector x is proportional to the original vector x, we label x as the eigenvector, and that proportionality constant as the eigenvalue. To find the eigenvalues, we rearrange the equation by bringing lambda x to the left side and setting the right side to 0. By applying the formula shown here, we can calculate the two lambda values, representing the eigenvalues. Although I'll skip the detailed calculation process, the symbol det here stands for the determinant, which represents the matrix's value. With the help of the formula and the example calculation provided in this slide, you can easily grasp the concept. In the previous slide, we found two eigenvalues, which allow us to determine the corresponding eigenvectors. Let's first consider the case where the eigenvalue is -5. In this equation, we input -5 for lambda and carry out the matrix multiplication. This will result in x2 becoming 0, and the eigenvector will be 1, 0. Next, for the eigenvalue of 1, we can use the same method of matrix multiplication. Solving it, we get the eigenvector 2, 3, 1. By following this approach, we can obtain eigenvalues and eigenvectors. If linear mathematics is not familiar to you, these calculations might seem challenging. However, personally, I believe that if you can understand the meaning of eigenvalues and eigenvectors to some extent, There will be no problems in studying dimensionality reduction methods, such as principal component analysis.